c'est un euphémisme de dire que je suis ravi d'accueillir Eric Smith en tant que conférencier dans notre série. Eric est un physicien théorique qui ne travaille pas dans la physique théorique. Être physicien théoricien n'est pas une description professionnelle, je crois, mais la description d'un état d'esprit à la recherche des principes. Et pour rendre des principes visibles parmi les variés phénomènes, il faut avoir un langage mathématique fusionné avec une compréhension expérimentée des processus naturels qui contraignent un problème particulier. Et identifier ces processus n'est pas un exercice mathématique, mais un exercice scientifique. Au cours de sa carrière, Eric a recherché des principes, non pas dans un, mais dans 3 domaines de recherche humaine complètement distincts. L'évolution du langage humain, où il a rejoint le regretté Murray Gell-Mann au Institut de Santa Fe, en rendant les méthodes phylogéniques, quantitatives et les adapter à l'étude du changement dans les langues humaines. Je crois que ça constitue une innovation majeure en linguistique comparée, qui est un domaine très conservateur. En même temps, Eric a rejoint le regretté économiste Martin Shubik à Yale. Et ensemble, ils ont produit un travail monumental sur la théorie des jeux, les institutions financières et la théorie de la monnaie, au service de la compréhension de l'organisation non équilibrée des processus économiques distribués. L'un des résultats de leur collaboration longue d'une décennie est un livre intitulé The Guidance of Enterprise Economics, The Guidance of the Enterprise Economy.
Of an enterprise economy, yes.
Paru en 2016 chez MIT Press. Si cela ne suffisait pas, Eric rejoignit le regretté Harold Morowitz de l'université George Mason pour aborder le problème de l'origine de la vie. Fidèle à son style rigoureux et honnête, Eric a absorbé une énorme quantité de chimie et a porté sa compréhension de la mécanique statistique des systèmes en dehors d'équilibre, des transitions de phase et la thermodynamique sur le sujet. Je crois qu'il en verra parler de ça aujourd'hui. Le résultat était aussi un livre spectaculaire intitulé The Origin and Nature of Life on Earth, paru également en 2016 chez Cambridge University Press. Souvent, quand je lis ou écoute Eric, j'ai l'impression d'entrer à un lieu de savoir contextualisé, disons l'économie, et sortir d'un lieu différent, dit l'évolution du métabolisme, en vertu des principes que j'aurais peut-être pu connaître, mais dont je n'aurais jamais apprécié le pouvoir. Et je ne pense pas que ce soit une coïncidence que les sommets qu'Eric a escaladés, il l'a fait en partenariat avec 3 géants, Murray Gell-Mann, Martin Shubik et Harold Morowitz. Tous ont décédé récemment, mais j'aime penser que tous ont cherché Eric et les 3 ont été modifiés par lui. Eric travaille actuellement la moitié de l'année chez ELSI, le Earth Life Sciences Institute à Tokyo, et la moitié de l'année chez Georgia Tech à Atlanta. J'ai toujours été balayé par sa clarté d'esprit et sa précision dans la formulation de la nature d'un problème. Alors, savourez cette gâterie aujourd'hui. Eric?
So, I want to thank you, Walter, both for the over-gracious introduction, but most of all for the opportunity to contribute to the program that you're developing here this semester. I also want to thank you all for participating in the seminar. It's fitting, given the monumental stature of Jacques Monod and his influence on the reputation and the vision of the Collège, that one of the things I'll be able to talk about today is a question that he first articulated as a modern problem in molecular science. Which aspects of the origin and evolution of life reflect the necessary action of laws, and which of them should be regarded as chance events and outside the domain of prediction? Even though this talk is in certain ways very much about the origin of life as a problem in physics and computation, I will not start with science that's explicitly computational. I'll start with very familiar parts of biological knowledge and planetary science knowledge, but in order to make sense of it, we will be led to paradigms of robustness from physics or complexity and cost that have their original home in computation. The lecture today will be organized in two parts, and each of the parts will be focused around a particular question. The first will be, what does an empirical analysis of life in its planetary context tell us about the kinds of information that are essential to the living state and their sources? The second part, and its question, will be, what kind of explanation qualifies as a causal theory of the origin of the biosphere? And then can we sketch some of its elements, even though necessarily it will be incomplete at this time? So the first part, a simple review of empirical knowledge that we have within biology that suggests a more complex theory of the cause for the structure of life than we usually hear. In understanding the nature of life, one of the things that I want to emphasize is that its information is of many kinds, and we should expect it to have many sources. Now, probably to everyone in this room, it will be very familiar how information from genetics is discussed and the role that it is believed to play in the evolution of life. I will not review that part here. I will be concerned instead with other components of biological information that are less often emphasized, in particular, the ones that are reflected in what is conserved in the biosphere instead of what changes, those that are organized around constraints or doing things in the way that is simplest instead of finding innovations for more complex ways. And in particular, I hope I'll convince you that these more muted kinds of information actually are the foundation that makes a Darwinian and a genetic world possible much later. So let's begin with some considerations in metabolism, the chemistry of the small molecules that are the starting point of everything. One of our foundation pieces of knowledge about biochemistry was the discovery by Hans Krebs in 1937 of what's called the citric acid cycle. In the direction shown here, it's called the Krebs cycle. This is a very simple molecular system. It has only 11 compounds, sometimes one of which is not shown. They're between 2 and 6 carbons in size. When we are taught this cycle in middle school chemistry, we're taught that it's an energy metabolism cycle that's important because we use it to digest fats or carbohydrates to get energy for the rest of our living processes. And in the course, we exhale CO2. That's why it's important to us, but that's not why it's important. A discovery in 1966 was the beginning of the realization of why it's really important. Evans, Buchanan, and Arnon found that in certain bacteria, the same 11 compounds are used in the same sequence of reactions, but they run instead in the opposite direction to the one that we use. Instead of taking in complex molecules, which are then broken down to the carbon dioxide we exhale, they take in carbon dioxide, which means that they fix carbon dioxide to build up more complex molecules. By 1981, Krebs himself had recognized that this direction of the cycle was likely the original one, and that the direction we use was inherited from it as circumstances on the planet changed. Within the next decade, other discoveries were made that have affected our ability to assign meaning to the citric acid cycle. One of the important ones was the development in 1977 by Carl Woese and George Fox of molecular phylogenetics, allowing us to create trees of the relations among organisms that exist today and to estimate what the common ancestors of different family groups look like. This is a modern version of the tree of life that's reasonably current for all of the species that we can compare. And as we have built this tree over time, we have learned that in the deep branches of the tree, where this compound or where this sequence of molecules and reactions exists, if it is run in a cycle, it is run in the reverse direction, the 1966 direction, not in ours. But much more fundamentally than that, even in the organisms that do not run this as a cycle, as shown here, they all possess the molecules and fragments of this pathway, and the reason they do is that every biomolecule that is synthesized, so everything that every living creature is made from, has the beginning of its synthetic pathway starting in one of only 4 or 5 compounds that are in this cycle. So from a modern perspective, we realize that it's not the energy metabolism role that makes the cycle important. It is the fact that with all of the diversity of chemistry in the entire living world, there's an incredibly small bottleneck of simple reactions and very small carbon compounds that are the starting points of everything. Now, this is an observation that's made by comparative analysis and statistical inference. It's not a theory of cause. If we want to assign a cause to the fact that this cycle occupies the position it does, we need to know more about planetary energetics. Now, something that is now common knowledge is that the electron flow on a planet like the Earth is organized according to its tectonics. We're familiar with the fact that volcanoes form around the edges of ocean basins, for example, the Ring of Fire here. Because continents are light, they float. The crust of the ocean basin is thin and mobile, and it can dive under continents, and as it does, it introduces water that causes the subsurface mantle to melt and be delivered to the surface. Now, the reason the ocean bottom crust is mobile in this way is that new crust can be formed at spreading centers. And this is where rock from the interior of the Earth, which contains its electron-donating early composition, is first brought into contact with the oceans and the atmosphere that are driven more oxidative. And so, in fact, the bulk of organized electron flow from the primordial deep Earth to the more recent surface oceans and atmosphere is concentrated at these places in the ocean bottoms where new crust is created and interacts with water. Now, since the 1970s, an increasing number of expeditions have been made to learn what these ocean bottom spreading center sites look like. Before the late 1970s, when they had never been visited, it was assumed they would be geologically interesting but biologically dead, because it was believed that all ecosystems depend on carbon fixation driven by sunlight, and there is no sunlight at the bottom of the deep ocean. When the expeditions were made, starting with the one by Alvin in, I believe, 1978, it was found that, in fact, these sites are both geologically interesting and biologically very rich, with very productive ecosystems, all of which are anchored quite quickly on bacteria that are using the electron transfer from the interior of the Earth to the surface as their primary source of biological power and their ability to fix carbon and perform other functions. With that observation, we were able to understand why a cycle like the reductive citric acid cycle would occupy the special place that it does. What I'll show you here is that the problem of carbon fixation in an environment that is electron donating, like the spreading centers, causes us to reevaluate classic ideas in biology like the struggle for existence. We think, following Thomas Malthus, of the problem of biology as being one of harvesting energy to do uphill work to build biomass. But in an environment that's electron donating, if you start with carbon dioxide and a source of electrons like molecular hydrogen, which is produced, in fact, to form all of the molecules of life is an energy releasing process as you add more and more electrons and reject the extra oxygens as water until eventually you have completely reduced the carbon to form methane and water as a waste product. So in fact, the reason biomass can exist in these environments is that it is a way to reduce a free energy stress. Now, what is true for molecules as a whole turns out to be true in an even more interesting fashion for individual carbon atoms within a molecule. This is the same Krebs cycle I showed you before with only the carbon atoms painted, and the tracks show you where the carbon goes from the time it enters in a fully oxidized form as CO2, as it is transported around the cycle and has progressively more electrons added to it, bringing it closer to the low energy state here. In fact, the cycle is self-amplifying, so this vortex that goes around is atom by atom providing an energy-releasing reaction sequence, and it creates complex molecules because these actually have a lower free energy to form. They're more stable than a one-carbon sequence would be between the fully oxidized and the fully reduced form. So in modern terms, this is what we think of as the causal account for such a simple cycle as this at the core of biology. Now, it's not only the energetics of biochemistry that we have reason to believe are anchored in planetary processes, but also the chemical mechanism. What I'm showing you on this slide is work from the lab of Joseph Morin at the University of Strasbourg. It's a very simple reaction system. It's driven by metallic iron in a water solution with soluble salts of copper and zinc. What he finds is that, in fact, complex molecules are generated. It's not an infinitely complicated reaction, but a relatively simple one that can be drawn here with only a few dozen compounds. But the remarkable feature of this reaction system is that the reactions and compounds that form overlap in large segments with the ones that biochemistry uses in the citric acid cycle. This entire system is not organized in the same way, and there are still important problems left unsolved. But what this work demonstrates is that very simple catalysts of a geochemical origin already go a long way toward accounting, apparently, for some of the things that biochemistry has retained and uses. Now, these are relatively simple compounds only of carbon, oxygen, and hydrogen. But similar results can be said of more complex compounds that include rings, double bonds, included nitrogens, and heterocycles, and so forth. This is recent, very beautiful work done in the lab of Bénédicte Ménès at the Institut de Physique du Globe, very close to here. What she is showing you is thin sections through the rocks that make up the mantle, the iron-rich part of the Earth just below the crust, in the course of being altered by water contact. And these micrographs show carbon that is included at the fronts where one rock is being converted into another rock by water alteration. These are preliminary studies. They're not exhaustive in their ability to analyze, but they indicate that the same, in fact, molecular species and certainly the same classes of molecules that biochemistry uses are formed in these alteration fronts. But more importantly, they are speciated with different classes of molecules being formed at different stages in the rock alteration, which shows that, or it provides circumstantial evidence that the architecture of biochemistry was presaged in geochemistry by the particular catalytic environments that are provided as minerals are converted in interaction with the surface waters. So I want to give you an interpretation that I think is justified and a little conservative, and then I want to follow with two comments that are not about the data I showed you, but that are relevant to connecting to evolutionary ideas. The interpretation is that biochemistry as we know it is much more intricately embedded in the geochemical context than was understood in any of the generations starting before about 1960s and 1970s. The comments I want to add to that are that this chemistry is particular and it makes sense in a geological context. If we did not know anything about Darwinian selection and competition, we would have a problem of predicting why this chemistry and not some other seems to be connected to the Earth. If we then learned that individuality existed and that there was Darwinian selection and competition, it would add essentially nothing to our ability to understand why this particular chemistry is found. So while it may be true that evolution is a part of all biological processes, that knowledge may not be relevant or helpful to explain certain features that are intrinsic to biology. If I can plant the seed of that doubt in your mind, then I want to follow with the argument that when we are looking for a theory of cause for the emergence and form and evolution of life, we should be looking for something that's more complex and more structured than simply a general mechanism called selection. Now, if I've taken away the Darwinian explanation for why things are as they are, we then need to ask, in some other context, are these metabolic features the causes of other things in biochemistry and life, or are they consequences of causes that arise at some other level? In most areas, I don't have specific things to say, but in one area where we can bring this question to evidence, we can say a lot, and that's the genetic code. So, a very influential figure in the way modern scientists think about this was Francis Crick, the discoverer with James Watson and Rosalind Franklin of the double helix structure of DNA. So Crick was the first one to formalize the idea that information flow in molecular biology goes from selection on DNA genes through the formation of RNA, messenger RNAs, to ultimately the creation of proteins that develop the phenotype of the organism that develops and then lives or dies and determines which genes are passed on. So it's approximately a one-way information flow with some feedbacks between RNA and DNA. This, of course, is true for certain kinds of biological information, and it's a very good leading order approximation for much of what happens in genetics and molecular biology. However, when we come to the problem of understanding genetic encoding, it leads us to a conclusion that I will argue for you is false. Crick was also a major player in the discovery of the genetic code and how it's implemented and understood. So when our body makes proteins, a messenger RNA, which is a string of RNA letters, is translated by complex molecular machinery into a sequence of amino acids, one amino acid for each 3 letters, and these are then connected together to make the proteins that are functional machinery of life. Now, in the early 1960s, it was not known how the 3-letter sequences were assigned to amino acids, as drawn in this table. It was not known what the mapping was. It was also not known how any of this conversion was made in molecular machinery. Crick was the first and the only one at that generation to propose, in fact, that the connection would be made by a complex molecular adapter and not due to some simpler process of affinity in the low-level chemistry of amino acids and RNA. When those adapters were discovered to exist and to be the tRNA, Crick's point of view seemed to be vindicated, but this is complicated machinery, and this is machinery that right now is encoded under the central dogma. So the view that this is the source of information then led Crick to prefer an explanation that he called the frozen accident interpretation, among the many different causal ideas that were possible at the time. And this is a remarkable paper in 1968 for the number of prescient ideas it includes that still are the basis of much of our understanding of biology today. So I'll disagree with a few points, but that said, the paper itself is still a monumental achievement of science. Crick's conclusion near the end of the paper is that the frozen accident interpretation in its extreme form would imply that the allocation of codons to amino acids was entirely a matter of chance, and he thought this was a preferable explanation. Now, not only the way the letter triplets are mapped to amino acids, but even what the amino acids themselves are, Crick said would have been largely due to historical accident. This view of historical accident went on to affect Crick's perception of the whole origin of life and the importance of accident and the lack of predictability in it. Here's what we can say now about the same question. This is the same genetic code shown before, and this is the citric acid cycle that I just showed you. From a metabolic perspective, we see immediately that the assignment of amino acids to codons is not at all random. In fact, for 3 families of amino acids, the first letter in the codon tells which backbone in the citric acid cycle the amino acid is made from. And if the first base is a G, it turns out that you start directly with that backbone and you put a nitrogen on. So not accidental at all. These are the citric acid cycle compounds. These are the backbones as they appear in amino acids, either the final ones or on the synthesis. If you look at the second base in the codon, you find out that it too has a lot of regularity in the modification that is made at the end of the backbone to generate the amino acid side chain. Again, not random. So there are many more regularities of this kind that I can show you, but I want to get quickly to the point that summarizes them all. The genetic code is so far from being random that it almost defines a kind of algorithm for the biosynthetic pathways of the amino acids. It's as if there were a decision tree, and the different letters in the genetic code at different branch points in the tree tell what chemical modification to make to a given backbone to arrive at an amino acid. Now, this is remarkable. We may not know the cause, but we can certainly say that in information theoretic terms, the genetic code is very compressible, and meaning that we can extract information from it by recognizing the patterns in it. And fundamentally, it is more compressible with respect to the amino acid biosynthetic pathway even than it is with respect to the properties of the final amino acid that determine the selective behavior of organisms. Now, at present, there is no causal explanation for why the code took this form. However, conservatively, we can say that a code that is correlated with synthetic pathways must be recording information from when the coding machinery was solidified together with the elaboration of those amino acid pathways. Selection for the function of coding, the ability to attach an acid with the right property to the right place in a protein string, can be part of the explanation for the assignments in the code, but it is at best an incomplete explanation of cause. What I want to suggest to you, though I can't argue that you must believe this, is that in fact, the elaboration of the biosynthetic pathways was locked in by other factors, like the geochemical factors, and they created a kind of scaffold that dictated the paths of least resistance as the code was forming. Now, that kind of circumstantial argument that I just made for you is the best that could be done up until about 15 years ago, and it's very unsatisfying. The reason it's unsatisfying is that the genetic code lies on the far side of a massive sequence of molecular innovations from small molecule biosynthesis. There's the transition to polymerization, there's the discovery and the control of folding of macromolecules, and above all, there's the origin of the ribosome and the translation system, which is a collection of extraordinarily complicated molecular components. As those have come to be better understood, we are learning that they too have structure of surprising kinds that suggest the interaction of chemistry, energetics, and the discovery of the fold as a new organizational form of matter, and that this complex causation actually continues the kind of causation that I was showing you exists in the small molecule world. So the first thing that you need to know to begin this story is that biochemistry is very strongly divided into stages. For the small molecules, which go up to fewer than about 20 carbons, the synthesis involves organic chemistry, it's diverse in its reaction mechanisms, and the properties of molecules are built into which reactions make them. Above about 20 carbons, and in some cases less than that, no new organic chemistry is used. All complexity of the reaction mechanisms is shed, and all larger molecules are made by only one reaction, which is a dehydrating polymerization, shown here as condensation, in this paper from the group of Lauren Williams. And I want to emphasize that many of these ideas are developed in this paper, so they're not new to me or this talk. The dehydrating condensation essentially removes an oxygen and a hydroxyl or a pair of hydrogens from complementary molecules to form a larger one. And in the larger molecule world, complexity does not come from the chemical steps, but rather from the sequencing and the organization of which things are polymerized. Now, as a chemical process, dehydration is not hard to understand. You can do it many ways. One of these is the one that Origin of Life people use in the lab. You simply reduce water activity by drying, and some things will condense on their own. Biochemistry uses two other mechanisms, which are called leaving group mechanisms. It can either use an already dehydrated phosphorus chain, which can then attach to molecules and leave, taking water with it, or it can use this sulfur motif, which is called a thioester, that performs much the same function. And there's a limited but extremely important set of mechanisms that are familiar from fermentation, which connect the phosphate leaving from the thioester leaving biological forms of polymerization. And of course, you can, in the geological world, connect either of these to ordinary dehydration. Volcanoes that lower water activity will give you anhydrous phosphate, and the electron flow that I showed you at the bottom of the oceans will generate these thioester groups. But while this seems an embarrassment of riches, it's easy chemistry to do, it creates a problem for the understanding of how biochemistry could have originated from geochemistry. And the problem is this. The great bulk of our polymerization that's done in biochemistry today is done using phosphates as leaving groups. But on the early Earth, while it's only moderately difficult to get phosphates in the ocean, it's very hard to get phosphates that are out of equilibrium enough that they carry dehydration potential because they interact directly with water. an important realization just within the last 2 years by the group at Boston University of Daniel Segre was that you can take the extant knowledge of biochemistry and you can remove the phosphate-dependent reactions, and it does not disintegrate into a set of unrelated fragments, but a skeleton remains which is powered by the sulfur motif that I showed you right here. And that skeleton contains much of the earliest structure of biochemistry. What I'll show you in the next few slides is a suggestion that this sulfur bioenergetics may have been related to the discovery of the earliest protein folds. Now, to show you this, I need to give you a little bit more background. We need to realize what the ribosome is. This is a magnificent megadalton weight macromolecule of RNA and proteins, and it is the machine that converts messenger RNA sequences into into protein sequences. The RNA in the ribosome is very unusual in the world of all macromolecules. This is a picture of what's called the secondary structure, the base pairing assignments, before they wrap in and fold in 3 dimensions for the large subunit of the ribosome. And what this shows is a sequence of background helices which are then extended by the insertion of new helices that branch out of them. If you look at the way these helices fold and then depend and wrap on each other, you find that the large subunit has the structure of an onion, and that onion can be decomposed into 6 phases, from the earliest and oldest at the center to later and later phases, the latest of which, phase 6, is where you first form a translation system. So, extraordinary point, we have a history of molecular evolution of this complicated molecule before translation apparently existed as a biological phenomenon. That's data. No one has an explanation for it at this time. But the accretionary onion of the RNA preserves something else that's fascinating, which is a history of the discovery of peptide folding. In the deepest core layers, amino acids don't even fold, they're only surrounded by RNA. Then you get the first beta hairpin turns and then beta barrels. Only toward the outside, where a translation system forms, do you get the first globular folds where you have interesting interactions of alpha helices and beta sheets to make complex functional structures. Now, hold the picture of this in your mind for just a second, because I want to show you that that same picture appears in a variety of proteins that turn out to not only be the ones in the ribosome, but also the proteins in the aminoacyl tRNA synthetases, the ones that attach amino acids to tRNAs, and in many of the core proteins that are used in sulfur-driven amino acid transfer from one component to another. This is a picture of the motif, this sort of alpha-beta-alpha sandwich that we see common to all of these, and it's the active site that's a little bit hard to see buried here in the methionine tRNA synthetase. A remarkable discovery was made by Hieronym Jakubowski in 2017, which is that the way the editing function of the methionine tRNA synthetase works to ensure that the correct amino acid is put on the tRNA instead of an incorrect one that's also present in biochemistry is in fact to use exactly the same mechanism that is used in exchanging sulfur and phosphorus in dehydrating polymerization. And in fact, it has since been shown that aminoacyl tRNA synthetases from both classes are in fact proteins for exactly this thioester exchange chemistry that we would need to explain polymerization early on. Jakubowski argues that the many protein families that subsume the ribosome, the tRNA synthetases, all of these thioester bioenergetic proteins should be understood as a superfamily that are unified around a basic domain, a basic architecture of these very earliest alpha and beta interactions. This is a lot of new material to take in out of nothing, and it comes from several domains. But I want to try to give you a picture of how we make an argument from this. In making sense of everything I've shown you, it's fundamental that we want to know about the problems that are hard, that are so hard they're almost unsolvable. Because if there's something that's almost unsolvable and there's only one way of solving it, such as sulfur bioenergetics, then the mechanisms that control that method of solution become a control point for the entire system that follows. In the case of the genetic code sulfur bioenergetics, folding, and amino acyl transfer, if polymerization was almost impossible because the disequilibrium is hard, the thioester becomes a unique thing in the entire periodic table because it can be formed by electron flow in the deep ocean where nothing else exists. The first folds to control the thioester feed back on the synthesis, polymerization, and their own feedstocks, and those are the ones that we see suddenly appearing in this horizon in the ribosome, but then populating the rest of deep biochemistry. The codon assignments, if that's true, come from something very dynamical. There's not a primordial soup of milli-urate amino acids waiting like partners at a dance to be assigned to tRNAs. Rather, the problem of synthesizing them and attaching them is a hard problem that may only have solutions in the context of the same folds that wind up controlling the tRNAs and inventing the translation system. In all of this, and this is an argument that Lauren Williams makes in these and other papers, it's not accidental that RNA is present with proteins in these early systems because there may be problems in controlling the folding of protein for which the presence of RNA is the only place that problem is simple enough to be solved. So, part one was a review of empirical evidence suggesting a complex causation. In part two, I want to turn more systematically to what we think a theory of the origin of life must be, and then show you that it handles in a quite natural way the diverse notions of cause that I showed you empirically in the first part. So what constitutes a theory in the origin of life? Much of what we hear written about reasons for the origin of life is what I would call scenarios. A scenario is a story for one thing that may have happened, and then another thing may have happened, and maybe we ended up with life. The people who publish these scenarios will often say, but we can never know which scenario is right because we can't go back in time, and how else could you know whether something is true? I will argue to you that that is a problem with reasoning by scenarios, but it does not represent a fundamental limit on what it is possible to know about the origin of life. So the 4 points in what follows that I hope to convince you of, if you only want a scenario, that's a thing that requires imagination and hypotheses about the mechanisms that can be involved. But if you want a theory of the origin of life, that theory will inevitably be about entropy, and it will need to be about robustness of the mechanisms that change entropy. Life's complex phenomenology suggests a sequence of hard problems of entropy rejection. Those are the ones I reviewed for you, like the problem of polymerization. Of course, if you have a distribution and you make it narrower, rejecting entropy, what you are doing is imparting information. And the information of life is diverse in its kind and its quantity and the mechanisms that bring it in. Now, entropy is fundamentally a concept about distributions. Changing the structure of distributions is not altering a microscopic phenomenon, but a whole process. And therefore, the ideas of robustness and phase transition, which we know in other contexts are fundamental to distributions, will also be fundamental here. So to begin to build this argument, I want to come back and revisit the problem of extracting metabolism from geochemistry. What was the origin of life? Of course, it was many things, but certainly it was two things. This is a picture of the volatile carbon compounds in the Murchison meteorite, analyzed by mass spectroscopy by Schmidt-Kaplan et al. Every dot here is a different value of the indicated property on a different molecule from this meteorite. The authors state that there are at least tens of thousands of different molecular compositions and likely millions of distinct molecules once you've considered bond topology and chirality and so forth. If we compare that to biochemistry, all of biochemistry in the less than 20 carbon size consists of only about 125 small molecules. And we also know that those 125 come from the even smaller set of 11 in the citric acid cycle. So the origin of life was a process of going from the vast complexity of what organic chemistry can do to the very small part that biochemistry actually reliably uses. Now, at the same time as it was reducing this complexity and diversity, it was, of course, doing the things we all know. It was innovating higher order structures. The idea that relates the reduction in diversity to the accretion of higher order structure is in fact robustness. And one of the best arguments for this comes from Herb Simon, a systems theorist from the 60s and 70s. Simon says, if you find a system with significant hierarchical complexity in its architecture, and you need to understand how that system could have formed, the only plausible formation theories are those in which you go through a sequence of intermediate steps that are stable. So in Simon's examples, if you're making a wristwatch, you don't hold all 1,000 parts together and put one screw on at the end. You make subassemblies, and then you join the subassemblies later. If you are Alexander creating an empire in Central Asia, you do not conquer one individual at a time. You can only do this if you're born in a generation when significantly advanced states already exist. You co-opt the leadership of the states, but you leave them to manage most of their internal affairs with only coordination with you. And in fact, when Alexander's empire ended, it didn't disintegrate into chaos. It largely went back along the lines of the states that had been there before his unification. If we want to apply Simon's very intuitively appealing arguments to the problem of the origin of life and entropy rejection, I think that we need something that looks kind of like Frank Drake's equation. The Drake equation, of course, was famous for trying to create coherence in a question like, how many civilizations, advanced civilizations, might there be in the galaxy or in the universe? How can you answer a question like that? You recognize that it has a dependency structure, where first there must be stars, and the stars must have planets, the planets must be habitable. Did they ever form life? Was it intelligent? Did it develop a technology? Did it escape the Fermi paradox? You may not be able to estimate most factors in this equation, but you understand that they have this dependency structure, and that enables you to have a coherent, coordinated discussion. The same thing should be true if we ask how we get from the diversity of the Murchison to the small diversity of biochemistry. I won't try to write the equation. I'll show it as a kind of cartoon, that there can be funnels, there can be filters, but in the following slides, I'll give you examples of what each of these might be. The first restriction is the one that I already showed you from geochemistry. From the Moran group or from the Menes group, we see that a very small number of simple catalysts can extract not only single molecules, but whole fragments of pathways or classes of molecules without the kind of specificity that we have in modern enzymes. The second and third factors that I want to argue to you exist require that we consider the problems of polymerization and folding, and they introduce the idea that I'll call fabrics of biology. I'll explain in a moment what those mean. Of interest to us will be the primary structure, the formation of a chain from monomers, and the secondary structure, the folding of that chain at the backbone level. Each of those is an entropy-rejecting filter of a particular kind. The important property that we need from them as fabrics is that the formation of each kind of structure takes something that was atypical in the inputs and creates it as a property that's typical in the outputs. That crucial change in what is typical from the beginning to the end, which computer scientists will all recognize from information theory, is also what defines a phase of matter or a transition between phases of matter. And a phase transition, interestingly enough, is a filter, but it's a filter that's only possible if you don't give it too hard a problem to solve. And that's where we engage with computer science ideas of algorithmic complexity. So these properties that I said we need from fabrics are, of course, familiar from the physical theory of the hierarchy of matter, which is organized according to phases and phase transitions. The important properties of our modern theory of matter are that the different phases are the modern notion of the assembly of building blocks into aggregates which are components that then become building blocks in higher level assemblies. In the hierarchy of matter, the fact that these occur by phase transitions is mathematically represented as a change in the representation of symmetry groups. What that means in common language is that a property that was not typical, that was rare before a freezing transition, becomes frozen in as a typical property that's made available by the freezing transition, and that makes things simple in the frozen state that would be impossible in the unfrozen state. And It is collective and cooperative effects that create phase transitions. That means both that they are separated and rare phenomena, but the very same thing that makes them rare also makes the phases robust. So the same ideas will be essential in biology. I want to argue that with a few examples. Biological matter, like the matter of elementary particles, is organized according to energy levels. The highest energy level is the covalent bond, which is 150 times kT. This is what is responsible for holding together the monomers in the polymer. An order of magnitude weaker than this is the hydrogen bond, and hydrogen bonds are what enable a polymer to fold into a secondary structure like this antiparallel beta sheet or the alpha helix for an amino acid. Secondary structures are very important because every colored dot in this picture is a charged residue that can form a hydrogen bond. In the secondary structure, every such thing that can be bonded has a bonding partner, so it forms a bond. And the structure in which those bonds form is also one that is relaxed in the backbone. So kind of like number theory, we start to see a single solution that satisfies many constraints concurrently, and that makes those solutions relatively rare in the world of molecules. Finally, at the weakest level, which is only barely larger than kT, we have what are called tertiary structures, the globular folds that I showed you, and those are stabilized by what's called the van der Waals surface, not by any single bond, but essentially by the adhesive effect of a whole collection of bonds on top of each other. The second Drake factor that I want to claim exists is the process of polymerization itself. It is an entropy rejecting filter because of the small molecules that exist, the only ones that can be polymerized are the ones that have groups that can be removed by dehydration in this way. It will be important later for folding because if we're at high water activity, hydrogen bonding turns out not to be possible if you're not polymerized because there's too much entropy of disorganization, of just orientation. So polymerization, if it happens at high water activity, makes hydrogen bonding possible where otherwise it would not. This creates a distinction between leaving group chemistry, like phosphate or thioester chemistry, and simply dehydration. Because in order to dehydrate enough to polymerize, since the energy of polymerization is much higher than the energy of hydrogen bonding, you just get aggregation, so there's no selectivity. But if you drive polymerization with leaving groups, then the formation of polymers winds up acting as a gateway that makes hydrogen bonding available only to the things that pass through it. The reason that's interesting, let me highlight this here. If we polymerize with a disequilibrium phenomenon so that we still are at high water activity and you depend on the polymerized state to hydrogen bond, then folding can turn out to act as another entropy rejection filter, and that's what I'll show you on the next slide. Polymerization itself can string anything together. So if I have a backbone here, maybe I can have several amino acids in a row, but then I can put in a nucleotide or a sugar in its place. I'll call these mixed polymers chimeramers. The reason I emphasize the complexity of secondary structure, like this beautiful parallel beta sheet here, is that chimeramers can't participate in that because the collective effects that make the secondary structure a phase of matter involve coordination in the backbone and the bonding. These are not available to random anything goes. But they have a free energy of formation, and just like Landauer's famous result that every computation has a minimal thermodynamic cost, we can use this free energy of folding as a rejection filter that will select the oligomers and reject the chimeramers. So it's a crucial problem that we know from computer science, which is the problem of sorting. If you have a random ensemble, there's an entropy of mixing that you can reject from that ensemble, but there's a minimum energetic cost to do it. The thing that's so beautiful about secondary structure, because it has a finite bounded energy, is that even if we do not have a complete Drake equation, a complete theory of the origin of life, if we depend on the formation of secondary structure to do a crucial sorting phase for us, to separate the amino acid oligomers from the nucleic acid oligomers or the polysaccharide oligomers, then that function places limits on how much chemical diversity we can accept from the planetary geochemistry. Because if the fold forms, it's a kind of refrigerator that rejects entropy of mixing. But if you take a refrigerator and you give it too great a potential difference for it to work against, it will run in reverse as an engine, which means that you will decompose your folded system. So in fact, the idea that a phase transition to a phase of matter, like folded matter, is a crucial part of our Drake equation for entropy rejection, says that if we ask about life on other planets, there can be crucial go or no-go decisions. If you have a planet that has too much molecular complexity or too easy an aggregation, then in fact you never get to secondary structure, you never sort, and the possibility of continuing the ladder of life stops at that point. You may still have organized chemistry, but it's a dead end. And these are the kinds of distinctions we want from a theory of the origin of life. The fold makes something typical that was never typical before. In small molecule chemistry, if I take a molecule, I ask about the reaction that formed it, and I say what reaction can apply to it. It's seldom the same reaction. It's usually a different reaction. If I say what was the energy to form it, and what is the energy that causes us to leave it to go to someplace else, that will typically be different. So the small molecule world is a world of ruggedness, where it's very easy to be some things and very hard to be their neighbors. That's why the Moran experiments give you such beautiful extraction of a few pathways instead of vast complexity. But if you think about what evolution is the exploration of nearby trajectories under very weak forces. You build a lot of machinery, you go through a whole lifetime, and then an individual lives or dies, and you only get a little bit of information from that. You can't do that kind of exploration if you're in a landscape that's so rugged that the substrate, the material, causes you to get stuck every step you take. There's nothing left for weak sources to support. So the possibility of a combinatorially large state space is atypical almost everywhere in small molecule chemistry. The reason we care so much about secondary structure is that the monomers that can form these things are the special gateways in the small molecule world where now uniformity becomes the typical property instead of the atypical property, and the combinatorial libraries or state spaces that we think of as enabling open-ended evolution first become a robust property. So I think we can associate the whole Darwinian world with the prior condition on the formation of these fabrics. This is an argument that Chris Adami has made in a very helpful form in an artificial life simulator where little bits of computer code compete with each other according to some criteria for being selected. What Adami shows here is that for a hard problem, like forming a self-replicator from random strings, the number of strings that can solve this problem can be so few that it can be impossible to find them under reasonable bounds of search because the strings are all uniformly weighted. The property of being a replicator is not typical in the uniformly weighted strings. He makes a point that's simple but still useful to quantify, which is that by such a small act as biasing the alphabet from which these letters are selected, he can make the replicators much more typical and thus findable. What we're trying to do in chemistry is that, except with the discrete change of phase made available by a phase transition. The same ideas continue at higher levels once evolution is possible. They take us to a story that's beyond the scope of this lecture, but I want you to know that it's there. There's a lovely body of work that's been put together over the years by Leslie Valiant, which aims at a theory of the learnable problems as a universality class like the computable functions. What Valiant is doing here is saying that reinforcement learning or evolution is a relatively blunt updating procedure, and therefore there are limits to the computational complexity of the problems that it can solve. So Valiant's ideas, which still have much more to offer than the part that has been developed so far, continue into the level of population genetics and other aspects of evolution, the things that we have said are the organizing principles, going from small molecules up through folds. So the big picture and the sort of messages that I hope to leave you with from this talk are the following. There's a foundation structure of life that lies in its matter, And that matter is below and before the Darwinian world that we're used to thinking of in terms of genes and natural selection. The deeply conserved universals of life are given meaning because each of them suggests a hard problem for which there were few solutions. So the job in finding a theory of the origin of life is from these universals to identify which hard problem they identify the solution to. I will argue that in general, once you take seriously how difficult entropy rejection is, we can say that even if we don't know what the theory is, any theory of the origin of life must have this dependency structure about entropy rejection, like a Drake equation, and the steps must be quantitatively compatible. So the needs for one step, like a phase transition, must be met by the outputs of the steps that feed it. If in the theory we have they are not met, we know either something is wrong or we're missing mechanisms. And so we can do what we expect to do in science, but which is so hard with scenarios. When something is missing, we can systematically do better than average at knowing where to look for the mechanism or what we need it to be doing. And then finally, phase transitions become important in biology for the same reason they were important in our fundamental theory of the hierarchy of matter. They take properties that were too hard to find or problems that were too hard to solve in the unordered phase, and by solving the primary entropy rejection, they make those just easy enough that then you have the ability to take the next step toward complexity. So these ideas come from many sources. I want to thank the organizations that have supported all of us over the years in working together on this, the institutions that are my home at this time, but I want to give particular credit to the work of Lauren Williams and Anton Petrov and Peter Penev, who have been the collaborators to teach me about the ribosome, and many of the ideas that I told you are sort of a physicist's reading of things that they see in the history of folding, and they're describing coming from the whole cloth of biology. And thank you so much for your attention.